Yesterday, I think I realized that we were very slow, but it's okay. And in any case, you must be having some more advanced courses. So at least one of the courses that goes a bit slow is fine. This I have shown many times, and I don't think I've explained why that happens, what happens. So just to start, as you can see, that we will look at some sort of a pressure equilibrium, hydrostatic equilibrium, and all that. You can see that this is now the water is in a perfect hydrostatic equilibrium. Yeah, you have turned the glass upside down, right? And it's not falling at all. Why is one question? And once it was in hydrostatic equilibrium, that means it could be supported by pressure outside. Why did it fall in the end? So these are the two questions. And it may seem somewhat ridiculous that these experiments are like not very controlled and stuff like that, but it is actually not so. The reasons are very interesting. So any guess what might be happening? Why was it supported first of all? I just took a glass, I turned it upside down, and held it by a paper. And yeah, this is I was only doing it. And you can do it much more controlled, nice, better paper, more clean and stuff like that, so that surface is not very corrugated and all. So you can see this once again. So the idea of all this fluid dynamics is that you understand some of these very simple looking things that are happening all over in astrophysics, everywhere. Okay. And I think I've shown this a few times, but never explained it. Yeah? Hoping that you will explain it for yourself. So as you see that this is very easily doable, and this is just held against gravity, no? In some sense, it's just floating, and it's just paper by it, just some cardboard, and I just slowly pull it out, and it falls. Why? After all, it was supported by outside pressure, right? So any guess why was it even supported? What was keeping it in the glass? What? Pressure outside was what? And when I turned the glass upside down, it was more like a vacuum. So there is a more pressure outside, less no pressure here. So pressure gradient, it's always we worked out yesterday, right? Negative gradient of pressure exerts a force, right? So negative gradient in this case points upward. So clearly the water is pressure supported. That's a clear proof of what we derived yesterday. So, but why did it fall? See, it was not supported by paper. That is why I am saying paper is just so that you can make this experiment that while you turn, you make sure that there is a vacuum above and all that. But now that the liquid column is supported, I can, and if everything is perfect equilibrium, after all, it is still true, even after you have removed the paper, it is still true, right, that the pressure outside is more than the pressure in the glass. Yeah. So the pressure gradient force is still upward. That is what it is supported against gravity. No? Even when there is paper, gravity is acting all the time. So gravity is not the answer. Density is one thing. So, but what will happen? So then what happens? Yeah, that's the right direction. So if I have a high density liquid, above and below is defined by gravity. Okay. You can always have below and above mixed up, but you generally define above with a sense to gravity, direction of gravity. So if gravity is pointing downward gravity, so then I can have a sense of above and below, and then I will say this denser fluid is being supported in above a lighter density. So it is in perfect hydrostatic equilibrium, but that equilibrium, this teaches you a lot of things, that while an equilibrium can be possible, you achieve an equilibrium, it need not be a stable equilibrium. Okay. It is subjected to instabilities, and these instabilities are prevalent everywhere in astrophysics. Whenever you are even supernovae blast waves, when they are moving, you must have seen by now pictures of Crab nebula and all that. Right? You must have asked, what are those fingers poking all over this supernova? You look at the ocean air interface, you can see that this is all curly. The surface, when you just stand by the beach, the flow is just curly. Look at the clouds. Yeah, there are all these patterns. Very fixed periodic patterns you see in the clouds. What are those patterns? All those things are actually governed by the same equation we already derived. In fact, much of these fluids can be treated as an incompressible. And what we derived yesterday, you ignore viscosity, which is true for many astrophysical cases. Viscosity is acting on a very small scale. Even for this problem, you can pretty much ignore viscosity. In any case, viscosity is by and large stabilizing the system, but working at a very small length scales. You are interested in astrophysics, so very large length scales. Viscosity perhaps not very important. So what we did yesterday was enough to deal with all this range of problems. Okay, so the answer to this we will derive today. Hopefully, I'll go fast. I actually don't know how to go fast. So we will try to be a bit, at least, somewhat fast. But there will be more questions today. So that now I think these sort of questions should anyway give you some sort of a sense. Viscosity, see, just within 3 lectures is very tough to introduce viscosity properly. I'll just say something. But by and large, for astrophysics people, viscosity is not really very important. But I'll just write this so-called Euler equation so that it's there on the board. And so by bold, I'm trying to write a vector, but let's be more explicit. Then I could write it minus gradient of phi. Okay, phi is your gravitational potential. Okay, so we'll keep it. For viscosity, I could always add a term which is kinematic viscosity, Laplacian of the vector. Okay, all it does, if you have done a little bit of Fourier transform, as people have covered, so you forget every term, forget nonlinear term, just look at this term and this term. This is a diffusion equation, heat diffusion equation, right? The Green's function, if you worked out, the Green's function is simply for each Fourier mode k is e to the minus mu k square t. That means it's a Gaussian looking Green's function, viscous Green's function. I could write, say, viscous Green's function, you write it like that. Again, just to save time. Okay. So anything, whatever happens, whatever is happening through other terms is basically decaying over a period of time because of finite viscosity. Right? So that is what it is. And as you can see, that the rate of decay is faster at larger and larger wave number. Wave number is inverse length, right? So I can always write a viscous decay time scale, yeah, is roughly 1 over mu k square, which is, I could say, of order some length scale, typical length scale of a system divided by mu. Okay. Another question I will ask, which I keep asking, I don't necessarily tell the answer. That is something for you to worry about. That whenever you have fan, nowadays AC has replaced fan, but if you have a fan, your experience is you turn on a fan and you switch off a fan. The air circulation, what happens to that when you switch off the fan? The air circulation, do you feel the breeze for a long time or it stops immediately? The air that you feel from the fan stops immediately, right? What is the reason that the air circulation? I can just have a wind flow here. Yeah, the wind, after all, everything is gone by this equation. Right? So any decay must involve viscosity. I can work out the viscosity for this room, given a temperature, given molecules, what sort of things are there. This is your decay time scale of any motion, yeah, that you have started a fan. So, what do you think decay time scale should be based on your experience? What do you experience that the decay time scale should be when you switch off the fan? Roughly. Seconds, minutes, days. Huh? Seconds. Somebody else? Any guess? Just take a random guess. based on your experience. I mean, I'm telling you that this is the equation, and we by and large associate viscosity with all sorts of decay, and you must decay the energy that was produced by the moving blades, fan blades, and it has decayed. The energy is decayed. Yeah. What is your experience of that decay time equation? Like roughly seconds. Seconds is one answer, but any other guess? So that's another exercise. Take a length scale of a meter, say, or your room, say 5 meter room, yeah, 5-10 meter rooms. Just Google viscosity of air in India, in Pune and stuff. It just depends on temperature. Yeah, work it out. You find the number is about 11 days. Okay, so fluid dynamics is full of mystery, and unless you have really understood those equations, there is no way you will really grasp what is going on. Okay, so what is your experience of second actually means in terms of viscosity about 11 days, 11 to 12 days. Okay, so where is the mystery? Why? Yeah. So the answer is of course in the nonlinear interactions, and that is where the turbulence enters. Even the air in this room, however still it looks, is actually quite turbulent. Okay? And then the whole dynamics and solutions, everything changes so drastically. Okay. So while this is a boring route to just write equations, derive and all that, but all the answers are ultimately lying in these equations only. Whether it's very fancy astrophysical objects or not, ultimately you have to actually fall back on these only if you really want to understand. So let's just quickly go through some very specialized flows. Again, due to time, I will not be able to tell much, but whenever the speeds involved and speeds of your interest, okay, the same medium can be compressible or incompressible, but you ask your question. Whenever the speeds involved are much smaller than the local sound speed, you treat the gas as incompressible. Incompressible simply means that the density cannot change. But what does it mean, the change? All you can ask for is d rho by dt is 0. That means del rho by del t can still be finite, by the way. It has to be just balanced by the spatial gradient. Okay? So this must be 0. That means saying statement that the rho must be constant or rho must not change means that it can change both in space and time in such a way that it cancel out. You understand? But I can treat like water, that rho is strictly a constant wherever, even when there are waves and everything, the density can be taken as a constant for water, in which case both these terms are individually 0. Okay? There is no spatial gradient of density, there is no time variability in density. So individually these are 0 for say water. Okay? For a lot of fluids that can be imagined, so that can be said. So the incompressibility, I will write simply as statement where divergence of V is 0. Another class of flow, which is quite interesting actually, and one can gain a lot of insight by simply looking for a quantity called vorticity. Has somebody written down this, discuss this probably vorticity? So as you can see, this is a curl of velocity field, this is the divergence of velocity. You can draw the vectors, you just bring your all knowledge from magnetostatics, electrostatics problem. Divergence is like lines moving through radial lines, and vorticity is some sort of circulation, right? This being 0, vector 0, yeah, so is another class of flow. So you call this an incompressible, and you call this flow irrotational. Reason we are discussing this is that suppose we start from an initial condition where the flow did not have any vorticity, meaning it did not have any circulation. As we will show very quickly, but in statement it is clear that as far as ideal fluids are being concerned, yeah, you cannot generate or destroy the vorticity. It becomes a conserved quantity. Okay? So that is something called Kelvin's circulation theorem, that the flux of vorticity through an area element is conserved. That means its Lagrangian derivative is 0. Okay? So it's a very powerful statement. All it means that all these so-called tornadoes, yeah, these big whirling motions that you have seen, what would you think if I told you that this is irrotational flow? by rotation, you are imagining. So let's say there is a flow here. Yeah. So those things we can anyway do. That is easier part. Try to understand. And if I want to construct a vorticity meter, I want to measure a vorticity. It can be done very simply. You just take two matchsticks, stick them like this. Yeah. Make a right angle and put them in a fluid. At any point, if the vorticity is non-zero, if the flow is such that there is a finite vorticity, if this omega is non-zero, yeah, this will, you just put it in one place, it will start to rotate, right? That is a measure, that's an experimental measure of vorticity. That you can say it is my vorticity meter, if it rotates, flow has vorticity, you can say that. Different points, if you put, it doesn't rotate, it is always pointing like that. You say that flow is non-vortic, it's irrotational. Okay. Now, again, there are lots of exercises. Look up and work out. By look up, I don't mean pictures, I mean work out equations. Full equations you work out and solve for yourself. Free vortex and forced vortex problem. Okay. So free vortex, tornado is an example where the vorticity is zero. Okay. It just simplifies the problem greatly because wherever a curl of a velocity is zero, I can always express that velocity as some sort of, people write minus, it's just convention, you can skip it, you don't like. So minus gradient of some sort of a phi. Okay. So it's called even a potential flow. Any irrotational flow is a potential flow because I can express velocity in terms of gradient of a potential for any irrotational flow. Why it is good? Because velocity is a vector quantity. These are three equations. Any vector quantity is very complicated. And if your situation doesn't demand, you better reduce your problem to some simple looking. Simplification will help because equations are inherently very complicated. If you really want to understand them through some math. So, whenever possible, the same vector field is now being replaced by a potential which is a scalar. Now your equation became very simple, right? Suddenly. Okay. So you can appeal to some general principles like this and then try to see if you can make some statements without really linearizing your system. Ultimately, we will say that you can't really manage with this equation, we'll linearize. But let's see how far you can proceed without linearizing. Okay. Bernoulli's system is, Bernoulli's equations are one such, which is not a linear system, but it is of course for very specialized system. Why is this popping up all the time? Okay, so let's just assume rho is constant. We are concerned with a steady flow. By steady flow means your Eulerian derivative is zero. Okay, the total derivative may still exist. Your Eulerian derivative is zero. That means you sit at one place, the quantity doesn't change. Eulerian is a derivative at a single place. At a fixed position, you take a derivative. That's Eulerian. Lagrangian, as you follow a fluid particle, that's your material full derivative. Okay. So steady flow, Eulerian is zero. Let's say rho is constant, divergence B is zero. I've already assumed incompressibility. You can do a lot by just assuming incompressibility. Compressible flows are far more complicated. This quantity here, that's why I've written it now here. So that's the ultimate go-to equation for anything. So this, you just use your typical vector identity, which is gradient of A dot B is some 4 horizontal terms on the other side, okay? But here A and B are both B, that's why you get gradient of B dot B. Okay, so you expand it and you get the V dot grad V, you can write in terms of curl of V, which is omega, right? Vorticity. So it's vorticity cross V plus a gradient term. We like gradient because then we can club all the gradient terms together, rho is constant. So I can write that the steady Euler equation already gives you V dot gradient of V is zero. That means all you have done, taken rho as constant, then you can take rho inside the graph. Right now, this should be written as gradient of P, is now you are saying is gradient of P by rho. Okay? It is not always possible, right? If rho was varying in space, you get another term, minus 1 by rho square grad rho. P by minus P by rho square grad P. grad rho. Okay, but given that the rho is assumed as constant, I can take this rho inside the grad. This already has a grad. From here, I'll get another grad v square by 2, kinetic energy term. I can put all the grads together, construct a quantity called a Bernoulli's constant. Okay, you must have seen this, but yesterday I was asking you. That is what you will get. That you will get something like v dot gradient of the b is 0. Right? Now, all that means is that b is whatever is this quantity, it is constant along a streamline. It turns out later on you work out that the particle paths and the streamlines are identical if the flow is steady. We have already assumed steady. So if you know the streamline, you know where the particle path is going to be. And if you've known the Bernoulli constant at one place, you can extrapolate and say that it is constant everywhere along that streamline. Okay, but it can be a different constant at different streamline. So it can have a distribution, but along a particular streamline, it's always a constant. Okay, that's the statement. It's a general truth, so long as some assumptions are made. Okay, completely non-linear, right? Further, if the fluid is irrotational, that means curl of E is 0. It may seem very restrictive that you are also assuming incompressibility irrotational. Many of the flows that you encounter actually satisfy both these criteria. So it's very useful. So if this is 0, this term drops out, right? This term here drops out, and then show that gradient of B becomes 0. And that's a very powerful constraint. Very powerful statement that your Bernoulli constant is constant throughout the whole flow field. So now it's very powerful. That entire flow field, you know that this quantity cannot change. So something changes, and now you know all your experience of venturi meter and everything. That suppose gravity is ignored, you increase the velocity, the pressure will decrease, and all that, right? Usual Bernoulli's theorem that you must have gone through. All that is basically coming from here. Okay, so let's go further. I just want to. Yeah, so something new. More I want to vary. Okay. Okay, this is a quick example. Everybody has done this. This I will not spend time. You can include the internal energy term, and you can write the Bernoulli's theorem in this form, where H is your enthalpy. Yeah, you know your enthalpy, right? So that is H specific enthalpy. We typically write in terms of per unit mass. It's a more useful quantity. Is equal to U plus P by rho. And if you have done the exercise I was mentioning yesterday about using these thermodynamic relations and derive something, you'll show that this is just Cp times T. Okay, U is Cv times T. This is Cp times. Very simple. Okay, so you can recast your Bernoulli's theorem in some different way. Again, given that this is V dot grad, it is basically a constant along that streamline. So this quantity, if you are interested in some sort of this. This you have anyway worked out how the pressure changes as you go deeper into the water, yeah, in a gravitational field. So all that the usual stratification, the pressure at the surface is P0, at height h below it is rho gh, right? And eventually tube also you have seen that if there is a flow, because the flow is incompressible, if I reduce the cross section, the velocity will increase. Right, mass flow has to be constant, mass flow rate has to be constant. So velocity increases, pressure drops, and that's why there is this. Okay, but this is taken from Feynman lectures. In fact, I highly recommend that you go through Feynman lectures to those two chapters. You would expect that V1 became V2, V2 became V1. So this height and this height should have been same, right? But Feynman is very careful. He has drawn this little smaller. Okay, so think about what would have gone wrong. Okay. So each figure or something, let's quickly do this hydrostatic equilibrium, plane parallel atmosphere. So what you imagine this Earth's atmosphere, imagine it plane parallel, flat, gravity is vertically downwards everywhere, so it's a slab. Yeah. infinitely extended slab in horizontal direction and stratified by gravity. By stratified, you understand, right? That your density, everything must be, you have a feeling that it must be going down. Yeah. How exactly it goes down depends on what kind of thermodynamics you choose. For an isothermal medium, it changes differently. For an adiabatic medium, it changes completely different. Okay. So that is something for you to work out now. But let's, for simplicity, but just to give an idea that how a simple hydrostatic, by hydrostatic one means that you simply set velocity term to zero. And then this part must be satisfied, right? This equation must be satisfied at all times. So this is zero. So this must be balanced by gravity. Yeah. If there is no gravity, you see that the gradient of P is zero, and then the P is homogeneous. P is same everywhere, right? That's the zeroth order solution. No gravity, hydrostatic, no velocity, P is uniform everywhere. Typically, one could say, okay, that's a separate discussion. I'll come to that because there is something I want to talk about. Little bit of GR. Now you must be learning about the equivalence principle and stuff, right? Must have heard the gravity can be made to vanish, right? Gravity is not a force; it can be made to vanish, and stuff like that. You must have heard by now, right? Huh? Yeah. So we'll see a consequence of that in a very different avatar. Okay. So this zero in Euler equation, you get this sort of an quantity. Phi I had written yesterday is just g times z. When g, scalar g is taken as positive, Ez is pointing upward, so minus Ez is pointing downward. This is your equation. It's a 1D problem, right? That is what is known as now 1D problem. dp by dz, meaning it doesn't vary in x and y. Yeah? So you can decompose, you can Fourier decompose only x and y in the horizontal plane, but you cannot now anymore do Fourier decomposition in z direction. Right? That also is clear. Yeah? It's stratified. Yeah? So recall what is the condition in which you can apply your Fourier transforms. Okay. So now z is out of equation. You can't really take simply the Fourier transform. No. Our equation of the state is such. Simply you have to plug it in. The equation of the state. Temperature is constant. It's an isothermal medium. So for an isothermal medium, which need not be the case, you can quickly solve. You get a logarithmic dp by dz is proportional to p itself. The rest is constant. So you basically can quickly solve and get P changes exponentially as you go up in height. It decreases exponentially, right? That's a solution. Now, the typical length scale, RT by G, is called the scale height, and you can work it out for Earth's atmosphere, about 8 kilometers or so, beyond which the pressure changes quite appreciably. But within, if you are dealing with layer, which is much smaller than the scale height, you can take your pressure as pretty much constant. But if you didn't assume this, it will be a completely different solution. That is something that you can try. Okay, so now let's come to vorticity and circulation. It's a very simple looking but very involved topic. Okay. And I can teach you a lot of things. In fact, our general common notion of lift, that why the aircrafts have lift, is actually wrong. Is actually not correct. That the velocity flows faster over the wing, and hence the pressure goes down, and the pressure that is actually not true. So the real answer lies in the circulation, the concept of circulation. In fact, but I will again not have time. Lift itself is about 3 lectures. Okay? But if you are interested, look at something called Kutta-Joukowsky hypothesis, or theory. But all that will require good working knowledge of vorticity circulation. Let's assume a barotropic fluid, which is also true for many systems, that the pressure is a function of density. So it's a barotropic. It's called a barotropic fluid, for which it just simplifies the problem that the vorticity equation I can take or write simply by taking a curl of this equation, right? Yeah. So if I take a curl of this equation, you can see that this term will drop out for a barotropic fluid. Curl of grad is 0, right? So this term anyway goes out of this. So you see that this equation is valid perfectly in a system with gravity. It's just that doesn't affect vorticity. So already you can see that the gravity is out of question as far as the vorticity is concerned, in some sense. Yeah. It's all hidden, and it is basically simply the operation curl grad is 0. For a barotropic fluid, when P is a function of rho, you can work it out that this term also drops out. So that's an exercise. This we anyway expanded previously in terms of gradient of E square by 2. So your curl will hit that, and that also becomes 0. And now you get term which is curl of E cross omega, omega V curl of E. So now this looks like a simple equation. So even before you do some very fancy theorem, you can already see that if a flow started off with 0 vorticity, now it gives an impression that it's a linear equation. At least it's linear in omega, that much one can say. That if omega is equal to 0 is substituted in this equation, it's a perfectly valid solution of this equation, right? We can spend some time here, that will save time in tomorrow for magnetic field. You will find that in an ideal MHD, the magnetic field obeys identical equation. You just replace omega by magnetic field, and that is your equation of MHD, called the induction equation. Okay, del B by del T is curl of B plus B. That is what is governing dynamos and generating magnetic fields in different systems, sun, galaxy, creation, everywhere. So there is a powerful analogy here, somewhat deceptive analogy, because this is a completely non-linear equation where omega is actually curl of V, unlike in case of B. So that's a really homogeneous equation, meaning linear equation, but this is not. Okay, that is linear in B. But in any case, you see that if omega was 0 to begin with, you will not be able to produce any omega, right? So that's good. Now you imagine all sorts of situations where tornadoes are being, it appears that tornadoes are being produced. The flow, you start off from a flow which is 0 vorticity. And suddenly you see that such powerful tornadoes are there. I mean, they create havoc, right? In the US and all, you see the news. Yeah? How come? Why do you see? When we are also claiming, and that is basically, at least again, feeling wise, we see that this is a rotating flow. It must have some sort of vorticity. So you should be slightly surprised that that flow is actually irrotational. There is no vorticity in the flow, but there is a circulation. So then, all of this is actually quite interesting. You define an integral quantity. Now, see, omega is a local quantity which exists at each point. Okay, and again, you can measure that vorticity by simply putting your vorticity meter and simply going and seeing if there is any rotation. Okay. Fine. Circulation is, on the other hand, an integral quantity, yeah, which is more distributed quantity. Think of it as more distributed. It involves a line around a closed curve. Where the closed curve itself, you see, it's written as a function of time. It's a big proof. Okay. So I will just suggest that you go look up the proof of Kelvin's circulation theorem. It's a very powerful proof, very important. Similarly, in magnetic field, you have Argand's flux freezing theorem. Statements are obvious that this circulation, which is determined by following a fluid circuit, that means the circuit C of T, it can deform in shape and it can actually move around. But the net circulation that these moving fluid particles have is conserved. Okay, so that is a proof that you must prove that the Lagrangian derivative of circulation is 0. Okay, so circulation is just conserved in ideal. All it means is I can take this V dot dr, use the Stokes theorem, and I can write this as curl of V dot ds. So any circuit will also have an area element, right? Yeah, and this can then mean that it's a flux, because that is maybe I have written. No, I have not written, but you can do it. So if I have some time varying circuit, closed circuit, yeah, which can be say this circuit, just like you create magnetic flux through an area, which is B times A, that area, bounding area. This area element is of course fluid, right? It's an imaginary area element that we're talking about. And if these are the vorticity lines, yeah. So if the flow is rotating like that, suppose the vorticity will be locally, it's just like your right hand rule. So it is pointing, just like J and curl of B. J is curl of B. Just how you imagine current and magnetic field, try to imagine omega and velocity. Okay. So it becomes easier. Alright, and now these are the vectors which are suppose going through a loop here. Yeah. So omega dot ds, yeah, I could write same thing as circulation, right? You understand? I just took this line integral and converted by using the Stokes theorem into curl of V. Curl of V I replaces omega. Omega dot ds is the circulation. So that's the same statement, right? Okay. I'm also saying, say in this example, it's called a free vortex. Okay. That is something you should work out. The surface of a free vortex. Okay. What is the mathematical shape of a surface which you will get if you simply took a glass and made a hole in the bottom so that the water can leak out? What is the surface there? Compare that surface. This is called a free surface or a free vortex. Just like in a bathtub, you must have seen or seen in bathtub, you see that the flow is rotating and all that. Yeah, so that's this is going. You can now put, okay, now this is like a flow in the bathtub. There is, in the language of black hole, one could see that there is a singularity here. And if you go to the center of the eye, that is exactly the volcano, that if you take a cross section of this tornado here, and or you were to see that from above, you'll find that this is basically hole all the way. Okay. Yeah, just like how you would imagine about black hole. Okay, the similarity. Now, again, your experience. What will be your experience if I were to put your vorticity meter at this point of the flow? Now you can see clearly that the flow is going like something like that, right? Yeah, and I put my vorticity meter here, here, here. Do you think that these will rotate? This will not be rotating. Okay, that is something you can work it out. To take the flow, typical flow of free vortex, yeah, typical flow of the free vortex that you can solve. Yeah, you try that, you can solve it. In fact, all of this is I expected you to show that the velocity, typical the velocity total, not only the v5, total velocity goes as 1 over r. Can you prove this? Yeah. So these are small looking things, but they hold the full answer to the understanding of what is going on. Okay. But anyway, so let's try to see that the two situations in which one I have a bucket and I made a hole, water can flow, you get a surface. Yeah, this is an air water interface. Okay, that means there is no water here when I'm drawing a surface. Okay, compared to I can do the same, and it's called a forced vortex. Try to solve a forced vortex problem. Okay, in which I can simply put the bucket on a rotating turntable. Yeah, what is your experience? What happens to the shape of the water when I take simply a bucket and rotate it with some omega? What happens to the surface? How does surface look? Ignore surface tension, ignore viscosity, any dissipation. When it is still, the water is flat, right? Surface is flat. When you rotate, what happens? Can you work out a shape? Mathematically speaking, we always know that there is some sort of a dip here, some sort of a rise here. What is the shape? Shape is a parabola, and you can work it out. That's a force vortex where your tangential velocity is r times omega. If I'm rotating it with an omega, tangential velocity is r times omega. Use that and work out an equation for the height. Okay, so you start from say z equal to 0. This is the shape here. Solve for h. Okay, h is height, which is a function of x in horizontal plane. What is this h of x? You find that's the parabola x, right? So h, height of the water above say initial z equal to 0 is a function of horizontal distance, and you should ideally be able to work out. Should take just 4-5 minutes. Okay, so work it out, and you'll find that this is a parabola, and this is anything but a parabola, right? Parabola is like a closed curve here, right? It's like there is no singularity, there is surface all the way, all through the center, right? But here it is hyperbola. So in a free vortex, it's hyperbola. In forced vortex, it's parabola. For a constant omega, you can see that the velocity actually increases as you go farther from the axis of rotation. Right? In this case, I'm writing velocity becomes infinity as you come closer to the center of the axis. Right? It's completely different behavior. Right? Why is that? So again, circulation must be conserved. It's an ideal. So now that is why you derive some general principle so that no guessing is required. This circulation must be conserved regardless of anything. Right? Free or forced. This is conserved. So what is the circulation about this axis? Simply 2 pi r times v phi, whatever is the v phi. That must be a constant. Yeah, that is a constant. You can see that the v phi on this v phi is your azimuthal velocity. That must go as 1 over r. Now you can ask or say that my v phi is 0. Suppose I started off with no v phi. Okay. What? But you are draining the fluid here, right? In any case. So then something must come towards the center. After all, you are draining the fluid. You are creating a free vortex. So forget v phi. Now your total, or what happens to the radial velocity? Suppose you didn't have any v phi. What happens to your radial velocity? Can you show that the radial velocity also goes as 1 over r? See, this is an incompressible equation. Okay. The only equation that you need to bother with is incompressible equation. The divergence of v is 0. This problem suggests a cylindrical symmetry. Okay. As soon as you see a problem, you find out what is good symmetry. Cartesian will be just too cumbersome and unnecessary. Cylindrical is a good symmetry, for some sort of symmetry. Phi. Yeah. So exploit that and write divergence of v, curl of v in cylindrical coordinates, spherical coordinates. Those things you must have seen, right? So just what is a cylindrical coordinate? That must be 0. After all, you have said there is no vz, there is no v phi. Yeah. So divergence of v reduces to that sentence, right? RVR. So clearly your r times vr must be a constant. So again you get that vr is proportional to 1 by r. Okay, so there is similarity both for vr and v phi. Okay. Fine, right? So there is a finite circulation, but there is no vorticity. And we wrote here that circulation is omega dot ds. We are saying now omega is 0, but vorticity circulation is not. Aren't you puzzled? This should puzzle you a little bit. I'm saying flow has no vorticity. Work out a flow and just take curl of that v. And then you will get that curl of v is 0. Okay. That exercise you can do. Okay. So omega is 0 for tornadoes and all that. Free vortex. Omega is 0, but circulation is not. Why? Because of the singularity that when you define circulation, okay, if I take the circulation by taking a closed contour here, which looks like a rotating fluid, suppose, I mean, after a tornado, there is no doubt that you can see almost circulation, right? You can see. If you were to take a contour or a closed curve to define your circulation, which does not include origin, okay, even the circulation will be 0. Okay, so there is no circulation if your closed curve spans the whole fluid, or it is simply connected surface in some language. That means there are no gaps, or there are no gaps in the flow. Once you include an origin, the vorticity and flow, as you see, is not even defined there, but you are free to take a closed contour here and work out your. So all the origin, it is of course independent of radius now. Once, because all the contribution to circulation is coming from just the origin, where vorticity is not even defined. Okay, but if you took a simply connected curve, the circulation here, everywhere you go here, it's always 0. It's only coming because of the singularity axis. So you work out the free surface again. Similar type of exercise. Now you are given these 1 by r. All you have to do is use the Bernoulli's theorem. It's a very powerful theorem. After all, that is supposed to be constant. Work out some pressure conditions and all. and show that the free surface is given by z, where as minus 1 by r square. That means it goes to minus infinity. And these are the real life manifestations of some of these things. These are some of the Helmholtz theorems. Again, it's taking a long time, but I've said roughly what I wanted to say. That if I take different cross sections, all I want to say that if I take a tornado and I take different cross sections, circulation is same for all these cross sections. So if you find that area expands, it must rotate faster. Oh, sorry, area expands, it must rotate slower. So that the flux, what is conserved is omega dot dA. So if your dA goes up, omega should go down so that omega dot dA is conserved. So that's one way to see. Okay, that's all is the theorems. It is independent of time, of course. Now, this looks very simple, but it's a very powerful concept. In fact, that is where one would say is the origin of generation of magnetic field, like dynamos. Okay, so let's quickly do it. It's actually not so thing. I'm saying omega times some sort of an area element is equal to a constant. Okay, yeah, and rho delta s and some sort of a length is basically also constant because mass involved. All you can say that the mass is conserved. These two quantities are constant. Rho is assumed as constant. It's an incompressible situation. I can simply take a division and I can write that omega is proportional to L. So convince yourself that the vorticity, the local vorticity, measure of vorticity is proportional to the length scale. Okay, meaning if I take some sort of an eddy, if I take a tornado, just think of a tornado, and you ask the question why people guess. There are how do you make prediction that the tornado is going to intensify in 3 hours? How do people make this sentence? You know that we know that this quantity is going to be defined. It's a singular, yeah, but it's at the heart of creating that very strong whirlpool and all that. Okay. If I take a tornado and I can predict that there is a cloud passing over, so cloud is trying to stretch the tornado. Cloud is stretching. As soon as you stretch, you thin down, so it becomes the eye is like closer. You thin down a vortex. As you thin down, because omega dot dA must be fixed, your omega goes up. Yeah? So local values of omega is simply proportional to the length scale. So all I have to do to make it more dangerous is to take that vortex and simply stretch it. Same thing will apply because omega and magnetic field share the same equation, same form of the equation. I just take a magnetic field element, embed it in a incompressible fluid. Okay, as you will see that this is a good enough approximation. All I have to do is just stretch that, and magnetic field is larger. So effectively, you produce the magnetic field. It will not hold unless you do something more. But to begin with, just for a starting discussion, it's enough to appreciate that all I have to do is to stretch that field line because the flux through an area element, after all, field lines are passing through some sort of an area element. It's an incompressible area element. That means the volume must be conserved. If I stretch, the cross section must go down. The local intensity of magnetic field or the local intensity of vorticity must go up. Okay, you have suddenly by doing almost nothing increase the values of magnetic field. So these are very powerful principles, and all the answers are lying in this very simplified. Viscosity will skip today. I want to do something different. Is there any question? I think, how long can I go on? Another 15 minutes is fine. Yeah. So please think of some question if you have. I will try to do something different. We talked about that glass experiment I showed. So let's look at some derivations. See, these are very classic topics. Okay, any textbook we will pick up, you will find that these are discussed. Every textbook will discuss it in different ways. Each textbook offers something. so, so even if it feels a bit rust, don't worry. Again, let's assume all that incompressible rotation. It turns out that this is not too bad. Okay. This is another problem for you to look at and think about. Yeah, it may take a long time to come up with an answer, but at least to appreciate the problem that there is a problem, that will not take much time. Just take a value of viscosity and work out. It is about 11. I think last I worked about 8 years ago. If the numbers of viscosity have changed, or easily about 10 years ago, I think. So, but I roughly remember it's about 11 days. Okay, so waves and instability quite often are simply described by in various textbooks. So let's start in a boring manner. That if I sit on a hill, there is a ball, and if I push it, it will not come back to its. It may be sitting at an equilibrium position. Again, it's like that water experiment. It was an equilibrium. Yeah, it had reached its equilibrium, hydrostatic equilibrium. Water was held against gravity due to pressure differences. Yeah, so simple enough sentence, right? Pressure differences can support against gravity. That is what is happening with stars are already. How are they stars support? There is a pressure. Stars are high pressure objects. They provide a counter force against gravity, and therefore the stars are there. Otherwise, they will just collapse. Right? Gravity will always apply. But those equilibrium configurations need not be stable configuration. So, if there is any perturbation, you look at the behavior of the perturbation and decide whether we are sitting at a stable equilibrium or an unstable. A lot of textbooks, I myself don't like it very much, but it's just easy to convey. Okay. You just push it a little and it just goes down the valley. So that's an unstable set. Okay. I sit in a valley, I push it a little bit here, it will oscillate and come back here. Yeah. So before it comes back, it will overshoot and oscillate. So when perturbations show a wave-like behavior, by and large, you can have an unstable waves that it has a wave-like behavior which amplitude grows in time. Okay, that is why I said that I don't really like this very simplistic idea because it can also be misleading. So the value of such figures is very limited, and you should be aware. Okay, so because quite often people say there is a wave solution stable. It's not necessarily true. You can have a wave whose amplitude just grows in time, and that's unstable solution. Okay? So, but by and large, again, for some simple discussions, if you find that there is a wave-like solution, particle basically tends to, there are restoring forces for the particle to bring it to the initial equilibrium position. That's more technical way of putting it. So, clearly, in every situation, you can start off with an hydrostatic equilibrium, you perturb the system and see how the perturbation behaves. It grows, decays, or supports waves. Okay. Now we see ocean all the time, we see air all the time, we see patterns in the clouds all the time. Clearly, you can treat Earth initially as in a strict hydrostatic equilibrium, okay, no motion, and you perturb, and you see that just that perturbation brings all this richness and beauty. Okay. So that is the topic. Again, for much of this, including for astrophysics, I mean, we don't really need these two heavy pipes. If no equation, at least I will show you some pictures, but somehow it doesn't move. Okay. It does do something now. Fine. So just imagine a general surface. Okay. This I can remove. I can draw the picture here. It's a general setting which is a little too excessively general for this discussion. But in a single shot, you will derive at least 3 or 4 types of instability. So that's why I preferred it. But This is not necessarily the best approach, but for a single lecture or something, this is perhaps okay. You think of a surface, yeah, I've already made it curve, but in an unperturbed case, you take a surface which is at z equal to 0, again, gravity pointing downward, okay, g is equal to minus gz, fine. So this you can imagine as, this is like ocean, yeah. It can also be any interface. But the point is that it can be any interface. It can be relativistic jets passing through intergalactic medium. Intergalactic medium where may be low density medium and your jet may be high density medium. At the impact, you have an interface. Supernovae expanding into interstellar medium, they offer you another kind of interface. So interface is a very general word, and what we are going to discuss applies to all such interfaces. Okay? But it helps to start in a simple manner that you assume an ocean. This is the water of density rho1 equal constant. This is air, density rho2. It's a constant, but a different constant. This can be C1, this can be C2. Yeah. We can even set rho2 equal to 0. Imagining that the density here is much larger compared to rho2, but let's keep it general. Okay. And so now assume there are even flows in those systems, right? I mean, jet passing through an intergalactic medium. Intergalactic medium itself could have some flow from other secondary mechanism, something. This can have a flow, say U1, yeah, which is a uniform flow. That's why U is a good word, uniform. U2 going in a single direction. Uniform means it's not changing, but this is an interface. So two-phase, different densities, different flows, but uniform in the same direction. Okay, just to simplify the problem. If it is too much, you can forget about this for now. Just look at like the problem of water. Two densities sitting on top of each other. One situation excites Z, the situation excites instability. It's as simple as that. If I have like water-air interface in this order is stable. If I perturb, you'll see waves, that is the ocean waves. Those are also called surface gravity. If I reverse this, that becomes unstable. That is what we did. That's a relative instability. Okay. There is no good reason to consider right now any vorticity and all. Anyway, you can even ignore flow if you want. Okay. So that means that any velocity can be written as a potential, gradient of the potential. So I can write it like that. So I can cast the Bernoulli equation more generally. So now this capital psi is the gravitational potential because phi I reserved for velocity potential. So phi is the velocity potential, capital psi is a gravitational potential. This is a very simple Bernoulli's theorem that this can be a function of time. Gradient, you integrate it. You write gradient of everything equal to 0. If I integrate, it is the integration constant of integration can still be a function of time in general. You can work out pressures and etc. such that you absorb everything and you remove your complication. You just keep it out of the way, but if you have it, it is easier to simplify the problem. Now, in terms of the velocity potential, if I have this as an x direction, so my coordinate system is this. This is x, this is z. Z equal to 0 is the interface of an unperturbed surface. Okay. So, if I'm writing total velocity as minus gradient of phi, yeah. So for a flow, and now there is a flow u1 below, u2 above. So if I ask you to determine the corresponding velocity potential below and above, this must be very simple, right? Yeah. So this is an unperturbed part. This is a total potential, and this is a perturbation. Just think of it being written as. So writing also takes a lot of time. And I don't know how will I cover MEF plasma now. Tomorrow. So, if I have total velocity written as some sort of a UEX, yeah, and plus a perturbation, which is a V1, yeah, V1 is also, the perturbation is also assumed to be irrotational, okay. So that means this also you can write as minus gradient of perturbed velocity potential, right? Yeah. So phi 1 and phi 2 correspond to perturbed velocity potential. Okay. They are already giving you some sort of potential. Even if you had no flow to begin with, that means capital U1 and capital U2 are 0, you will perturb and have phi 1 and phi 2. Apply divergence of V to 0 strictly to both perturbation and unperturbed part. So you get a Laplace equation. Yeah. Divergence of V being 0. This is for the fluid below. This is for the fluid above. They will both individually satisfy Laplace equation. This is some sort of a necessary detail that you must do, and then you can write the total flow below in terms of velocity potential, total flow above in terms of velocity potential. After all, you are trying to, what is the goal? Yeah, goal is to determine if the perturbation oscillates, grows, or decays in time. Yeah, z equal to 0 is an unperturbed location, but when I at a given time, the height of the interface from z equal to 0 level, we denote it as, let's call this as xi, which can be a function of x and t. X is horizontal, so it is different height at different locations, right? It can go plus and minus about z equal to 0. The height, just like I asked you with the surface of parabola, right? For a force vortex. Similarly, everything started from z equal to 0. The xi is the height of the interface with respect to the z equal to 0 level, so plus and minus, and can depend on x and time. That is what wave is, right? So now you perturb it, you can identify, mark the interface and measure the height of the interface with respect to 0 level. The goal should be to relate these phi 1 and phi 2 with this interface. Z equal xi of xt is the perturbed position of the interface. So if you can relate these two, you get some differential equation and solve. Okay, so it is actually as simple as that. How will you go? Okay, you have to write, I think it will take a long time to explain, but see, whenever you are writing a surface, the whole surface is now moving. So this is at time t, and at time t plus delta t, the surface would have moved somewhere, right? Somewhere else. But you can trace the particle. Suppose you label, you put a dye on a fluid element, and you trace the motion of that fluid element as it is moving. So this fluid parcel, this is your fluid element, take it below surface, you can take it above surface and solve it for both. You do matching. Yeah? You write at the surface, the fluid below the surface and fluid above the surface, they should both move with the same vertical velocity, right? Just below and above the interface. They should both have the same. So that's one matching condition that gives you set of equation. Pressure above and below should be the same. That's another matching condition. That's all. That is what you have to do. It just looks a bit cumbersome and ugly almost. But then the way to do is you identify a fluid parcel which can be at location B at later time t plus delta t. How will it go from A to B? After all, because of velocities. It could have gone in x direction by x component of the velocity field. It would have gone up or down by the z component of the velocity field. The z component of velocity field, yeah, is entirely determined by the derivative or Lagrangian derivative of this displacement vector. Displacement you are measuring only with respect to z, right? And if I write d xi by dt, that is your velocity, right? Vertical velocity, right? You do it, you match the vertical velocity for fluid below, fluid above, that's it. Okay, so that is the philosophy of calculus. Okay, so let's focus on a fluid element just beneath. Its vertical velocity, you can write vertical velocity is what? It's any velocity is gradient of a potential. It's perturbed because to begin with there was no vertical velocity. Perturbation gave you a vertical kick. If you were writing for x component, you will get that un factor also. That is what is the origin of here. Okay. So this is in terms of potential, but I want to express that in terms of displacement of the interface. Okay. So clearly, this is the vertical velocity. It should be same as total Lagrangian derivative of xi, and those two must be same, right? So I can equate this to a Lagrangian derivative of xi, right? Lagrangian derivative is not u dot grad u. You have to neglect all small. So that is basically linearized. You have to show this that when you are taking quantities like suppose u xi 1, and if I get another small quantity, suppose something like xi square order term, yeah, that you throw. So you linearize in perturbation. If the mean type quantity u hits xi, you keep it. But if a phi 1 or quantities of order phi 1 and xi 1, if they are multiplied, you ignore because that's a non-linear. Okay, two small quantities multiplied gives you further small quantity. Okay. So linearize, that is called linearize. Linearize in perturbations. Okay, that is also you should keep in mind. You do this for the fluid below, fluid above. At z equal to 0, that's also, see, you are determining at not necessarily at z equal to 0, but then you work it out. That's another exercise that you show this that d xi by dt at z equal to z is approximately equal to d xi by dt at z equal to 0. Okay, so I can replace all statements at z equal to z, which is more general, to z equal to 0. All that is valid if your initial perturbations are small perturbations. Okay, amplitudes are small. Clearly, you can see that d xi by dt, when you will expand, you will get terms like u plus grad phi 1, right? In your u dot grad v term, u dot grad psi term will involve two terms: mean flow plus perturbed flow. Perturbed flow hitting SI, it gives you another non-linear term. So you throw it and then you can write it. All that will be needed for you to proceed. Okay. Then it's a stratified system, is it? But in x and time, I can seek modal solution, so called plane wave solution. So this is again like a Fourier decomposition. Okay. So I can seek a solution for the displacement, which is sinusoidal in x and time. Okay. Now, if omega, as you see, how will you do the game later? Okay. So I'm seeking a solution which is, I'll just show you, okay, that I'm writing it like minus I omega t. Okay. Omega can be real and can also have an imaginary part. Okay. If omega has an imaginary part, it can decay or grow, right? Why? I can write it here. So this will give you e to the minus I omega real t, which will always oscillate, into e to the I, if I multiply I square plus I. So you get plus omega I t. Now, this is not an oscillatory term. This is an imaginary part of omega. And if omega I is positive, you have unstable growth, exponentially growing solution, right? E to the plus omega I t. If real part is non-zero, you have oscillatory growing solution. Okay, it will grow and oscillate. Omega is unstable, exponential growth. Okay, if omega, so there are three situations. Let's remove the clutter. If omega I is, this is what you have to just get. That all that requires is somehow you get a dispersion relation and look at the problem. Okay. Now that is a long route, and that stable you can say it decays. Let's not call it stable. It is stable because it decays, but better to just say decay. when omega I is 0, oscillates. The reason I am writing it like that because one of the slides I wrote oscillate, decays, grows. So that is what it means. Oscillate, decays, grows. Okay. Yeah. So in different situations, depending on the combination of mu 1 root 2, you may get one of these. Okay. And that decides for you the instability and fate of perturbation. So anyway, you can see solution like this, but for phi 1 and phi 2, you have to be careful because it has to satisfy Laplace equation. It will have z dependence as well. Okay, it will have a z dependence, but you can work it out very easily. You take plane wave solution in x and time, multiply by a z dependent amplitude, phi 1 and phi 2 are the perturbed velocity potential below and above the surface. Put it in the Laplace equation, work it out. Impose a condition that the perturbed potential must go to 0 as infinity, plus infinity and minus infinity. So these are the two boundary conditions. Okay, apply that, you get equation like this. Very easy actually. So you appeal to Laplace equation, you get B, C, A, 3 unknowns and 2 equations. Okay, so you're still stuck. Okay, now very simply you now do matching of pressure at the interface and you get third condition. So that solves the problem, right? So that means the pressure must be continuous. What I'm saying here, the derivative, z derivative of pressure at the interface, z equal to psi is the location of interface, yeah, at any x. Psi is a function of x and time. So it's a complicated object, but it must be true that pressure is continuous through the interface. Okay. So all you have to do, use again your Bernoulli's theorem here. This thing, you can write pressure for below, pressure for above, put everything on the right hand side, and just equate it. Okay. You have already worked it out, right? All these phi 1 and phi 2, everything you now know. Everything is in control. Yeah. Everything is right now in control. You will write down an expression. Of course, you have to linearize in perturbation. Whenever you find a product of two perturbed quantities, phi 1 times xi 1, throw. Xi square, throw. Phi square, throw. Okay. So just linearize in perturbation and match the pressure below the surface, above the surface. Yeah. You have to do things like this. It's quite a lengthy calculation from that step to here. But again, I knew that it will take a long time if I had to do the whole thing. But if you try it, you will get it very simply. You'll find that all your kinetic energy terms and all cancel out. That's very good. Now, if you have a very simple looking equation, phi 1, phi 1, you can just put your exponential these solutions here. So all the derivatives will become algebraic, right? Del t of phi 1 will give you simply minus I omega. So the differential equation becomes an algebraic equation. And that gives you dispersion relation. Okay, that is what our goal was. No? Dispersion relation is the relation between the frequency omega and k. These were the solutions we were looking at. Omega as a function of k is the dispersion relation, and that tells you everything about the nature of perturbation and the fate of perturbation. Okay, so you can find that this is the same equation. Yeah, this combined with the other three, when you eliminated A, B, and C, will give you a simple quadratic equation here. You will get ax square plus bx plus c type equation if you write for quantity omega by k. So it will be some a omega by k square plus b, where a, b, and c are completely determined by the gravity, by flows, stuff like that. Right? So there are two roots, and you can simply solve for the two roots. That is your final discussion. It's looking very ugly, right? But it can be simplified very simply. Just set if you are interested in air and water and you're not interested in Kelvin Helmholtz, no shear, no flow, set all u1s to 0. So this whole thing goes, you have a very simple looking equation. Okay, so I'll take maybe 2 more minutes and I'll tell your next instructor to give you some more time for break. Otherwise, we can't begin any magnetic field tomorrow. Okay. So, let's look at some pictures. Surface gravity wave. Okay. Examples of ocean waves, F modes on the sun. Yeah. Those are all examples of surface gravity wave. This is the wave. What is the dispersion relation? You set U1 equal U2 equal 0. Practically, you can say ρ2 equal to 0. your omega is actually, yeah, omega square, I can write as, so that I'm not writing the two roots. You see that square here, so there are two roots, g times k. Okay, k is horizontal wave vector. That also should keep in mind. In fact, it's better to put kh. It's horizontal wave vector. The wave is basically translating in this x direction. Omega square is gk, it's a parabola. You can work out group velocity, phase velocity. Phase velocity is what? Omega by k goes as, yeah. How does it go? I can write omega is square root g and k. Square root g I can just in tilde absorb. Then what happens? 1 by root k, right? Does it make sense? For omega by k goes as 1 over root k. That means a different phase velocity is a function of wave vector, wave number. What are such waves called? Waves. See, each k is a single wave, right? I mean, this is true for each wave. So if k is large, you are talking about large wave. Yeah. So if I have a large k, this is like large sinusoid. Small, sorry, large k is a small sinusoid. Small k, large wave. Yeah. So small k, your phase velocity is larger. Yeah. So the largest wavelengths travel fastest. Okay. All these are somewhat should be surprising to you. That's how when you go surfing and all, you can see all these behaviors. When you just go to the beach, many of these things you can experience. Largest wavelengths are traveling fastest. Okay. This is a parabola. The shape will be like that. Yeah. Omega of k will go like that. It's dispersive. That's what I wanted to hear. That different waves or waves with different wavelengths travel with different speeds. If your phase velocity is independent of k, you call it non-dispersive wave. Okay, tsunami is an example of a non-dispersive wave. That can come from just this. Okay, there is a tan hyperbolic term. If I bring in the right now, it was assumed that the medium above and below the interface is infinite. But if I restrict it, you get correction here, and you can write down the shallow water equation. These are called deep water equation. Then you can write down the shallow water equation. Tsunami is an example of that. That is non-dispersive wave. That's why destructive. Dispersive waves basically they disperse. Yeah. Okay. Now, so that is directly from this general dispersion relation, right? This has now everything. All I did u1, u2 0, rho 2 equals 0. So rho 1 by rho 1 will be cancelled out. So it's only g by k. Okay. I can now take Rayleigh-Taylor instability, which means I now take fluid which is heavier above. That means rho 2 is greater than rho 1. Okay. Rho 2 was fluid above, right? Rho 2 greater than rho 1 is now the situation of the glass. Yeah. So now if you see here, for omega to have an imaginary part and offer growth, because this has two roots, so there will be always a growth possibility. So what will you get? Suppose u is 0 still. Rayleigh-Taylor, we forget about this term, this term. Only look at this. If rho 2 was larger, in your square root, this is negative. So it's a square root of a negative, you get an imaginary contribution here, right? That is your Rayleigh-Taylor instability. Okay. How does it look? Looks like this. That is exactly. This is the fingers in the supernova. This is a Crab nebula. Yeah. From supernova, you can notice these fingers, right? People show these pictures. All it takes is basically solving all these equations, and then you make sense of fingers developing in the supernova shell. Why? Now, when you guess, see, Rayleigh-Taylor instability means that you have dense fluid on top of light fluid. Okay, that is when I am saying that in this situation, this applies. Okay, how? So that is something you have to think. You have to invoke a bit of your GR to think about it properly. Okay, but I leave it as an exercise, and we can discuss outside if you have energy and time. Okay. Okay. Now, a single finger in simulations can be shown that blue is a denser fluid on top of a lighter fluid. top is always with respect to gravity. Okay. See that the finger developing. This is a single finger. But as time passes, you see these secondary structures right here. That is Kelvin-Helmholtz. So in most systems which will offer you Rayleigh-Taylor will always have also the Kelvin-Helmholtz. They come together. Why? Kelvin-Helmholtz involves motions. It's basically two layers shearing past each other. Yeah. So then for Kelvin-Helmholtz, we will not ignore U1 and U2. And you can now see that I can choose a combination so that this remains negative, right? Yeah. And if that is so, that means this term, whenever this term dominates over this term, for finite U1 and U2, we get an instability, that is Kelvin-Helmholtz instability. How does that look? This is Kelvin-Helmholtz here, circulations. Or when you look at ocean, river, air, water interface, astrophysical jets, this is quite interesting, onset of convection at thin length. When you are heating your teapot, you have to boil water. The water which is in the bottom is thermally expanding, becomes lighter, and the fluid above is basically denser momentarily. No? That leads to circulation. And that is how you are boiling tea. Okay. Onset of convection at thin layer. That's an example of Rayleigh-Taylor. That involves an example of Rayleigh-Taylor. Okay. So Kelvin-Helmholtz in clouds, you can see patterns like this. That is simply that layers have finite velocities, two different velocities in two different layers of different densities. You will always see some upturning motions. Okay, these are excited by Kelvin-Helmholtz. The conditions are obvious now. If you have derived a general expression like this, whenever you look for an instability, make sure that you want an imaginary term. Whenever that is not satisfied, whenever this so-called radicand is positive, you have a wave. When this radicand is negative, you have an instability. Okay. Now U1, U2, Rayleigh-Taylor or surface gravity. With U1, U2, Kelvin-Helmholtz. Kelvin-Helmholtz, Rayleigh-Taylor come together because as soon as you excite a Rayleigh-Taylor, this fluid is falling. Now, this fluid has motion, the fluid below is at rest. So you can have a situation which is U2 is 0 but U1 is finite. Okay. So now, at this interface, this fluid is moving down. It will be subjected to Kelvin-Helmholtz instability. Okay. Now, that's a separate question for you. That why Crab nebula figures you can think of in terms of Rayleigh-Taylor instability. Where is Rayleigh-Taylor instability here? After all, there I didn't even invoke any motion. Sorry, boss.
Canteen manager is the boss.
No.
No, actually, you take.
No, not for me, but give them some break. 5 minutes.
Yeah.
Yeah. They would never come.
No, you finished the topic.
No, I'm done. Yes, luckily. Okay, questions you can talk outside if you have any. If Santosh is watching, stop recording please. Where do you record? How do you stop? No. Oh, I didn't even share this thing. Good.
What people were doing on that?
I have no idea. I mean, oh, that was very bad. And I actually didn't notice that I stopped sharing. Okay, no problem. What? I was not watching. Somebody should have called me. Normally, yes. No, I mean, Santosh or somebody, they would have seen a comment. They should have just called me. Where I don't know, but they should have called me.
No, it was visible. I checked that out later. This
in YouTube, but in Zoom participants.
No, Nishant, it was visible.
it was visible.
Visible. Oh, very good. Then why?
Yeah.
You can leave it. Is there any question from online participants?
Not so far.
Okay, good. Actually, yeah, I forgot. I must have. Yeah, I would have guessed that somebody would have told us. But he's not.
Actually, it was.
Huh? No, but the later things, they were also. Okay.